interns who are giving presentations for their internships, representing for the math department. She's going to give a presentation actually for Aubrey, since Aubrey's here, giving a presentation to you on her next internship. I'm trying to think if there are any other details. See me if you're missing anything. We can figure out how to get it done. Fabio, you're still here.
I need you.
You need me?
Yeah.
I'll be available for you in a minute.
Yeah.
And we'll step outside the hallway. Yeah. Real quickly, anybody else want to wave at each other? It's nice to see you all. It's been a fabulous year working with each of you. I'm in the midst of hiring for new SPTs for next year. All of you will be given the opportunity, provided that you have over a 2.5 grade point average, to interview to become a mentor for the next incoming class of OpSTEM, and it pays $1,000 a semester. Actually, not all of you, only the LSAM students. So if you are part of the LSAM program, it's a piece of the LSAM program. But we are looking into how to build that out into OpSTEM on the whole. So keep your fingers crossed. So watch for that. I hope that you all have done well this semester. I know that it's harder than you think it is. And we're about to have summer break. Who's working summer break? Who's taking classes summer break? You're in good company. You're in very good company. So we'll be around. It'll be a lot quieter in the math department, but feel free to continue using the Math Drop-In Center and all the resources that are there for you, including me and Dr. Carver and all of our STEM peer teachers who are here, there, and otherwise. Even Aubrey's a fabulous resource. She's been serving as an advisor for some of the, anybody have Aubrey as an advisor this year? No? She's been one of our program assistants, just like Beth Ann and Maggie, who have helped with some of the years advising. So it's been really, really nice. On that note, I'm going to introduce you to Aubrey Loki, who is she'll tell you about herself, but I want you to appreciate Aubrey's fabulous outfit.
Well, that's the nice
yes.
guy.
Space.
Aubrey has a strong interest. She's a physics and CIS, right? Computer engineering major, who has a very, very strong interest in basically dielectrics under conditions where they are exposed to high levels of nuclear radiation that she'll tell you about. It's really fascinating. It's fascinating stuff. Well, basically, it's how we deal with contaminated sites that need to be cleaned up without putting people in them. So it's interesting stuff. This is her strong interest academically. And as you go through your education programs, use Aubrey as a role model. You can get interested in the most esoteric or quirky or unknown thing, but what that does is that makes you really useful and follow your creativity and do what you want. Aubrey's going to share with you her experiences as an intern at NASA. And if you have any questions, please ask her. If you haven't met Aubrey before, she's very nice, she's very bright, she's very engaging. She is our space princess. So enjoy.
Thank you very much. Good morning, everybody. I wanted to tell you about my experience at NASA Glenn Research Center. It was really cool. I also want to explain to you a little bit how you can apply in the application process and things that you need to look out for if you too want to get involved with the LRCIP program at NASA Glenn. So I was actually Avionics Software Imaging and Data Acquisition Support. That was my official title. What I did was set up data and acquisition imaging systems for an experiment, which I will explain to you in a little bit. I was working with the microgravity branch, which is where they study all kinds of physical properties involved with like microgravity. So when you're in orbit, when it's not, there isn't actually a thing such as zero gravity, but microgravity, there's very small effects. So the microgravity branch at Glenn studies these effects. The project that I worked with is called the Flow Boiling and Condensation Experiment. It consists of 3 modules, which are going to go up to the International Space Station in 2020. I worked primarily with the flow boiling module, which you see on the bottom. But I also got to do some imaging with the condensation flow visualization module. The three modules are basically designed to study either condensation or flow boiling. Condensation effects actually are quite different in microgravity and space, and so are flow boiling, where you essentially are flowing a boiling fluid through a channel for either cooling purposes or if you're removing a boiling fluid in an engine system. So the top one there, with all of the crazy things on top of it, is the heat transfer module, which is one of the two that will be going up to the International Space Station. Unfortunately, the flow visualization module had to be de-scoped. But the heat transfer module is a pure data module. It only collects pressure and heat data from the experiment. And same with the flow boiling, although flow boiling has a visualization component as well. So it's the little one on the bottom, is the one I work with most. So as far as the flow boiling module, they do 3 different test configurations on the ground before they send it up into space to see what kind of data points they can expect when it's in orbit. The vertical downflow configuration is essentially it flipped up on its head. The horizontal is just kind of, as you see, this laying a line, and the vertical outflow is flipped the other direction. We took probably 6 or 7 different test points at each configuration. And it was extremely cool looking. It's bright blue because of the way that we imaged. I'll explain that in a little bit.
Okay, so it's not just like.
No, it's not just aliens, but it does look extremely like intimidating. It was very bright, very bright. You had to actually put up we had to put cardboard in front of it to not go blind from the LEDs. It was very bright. So what the actual point of this experiment is, we are studying microchannel cooling and especially critical heat flux. Now, critical heat flux is a type of failure situation when you have something, when you have a flow cooling. So if you're using a liquid cooling system, the goal is to remove that heat and change phase in the fluid, because a phase change, I don't know how many of you are in physics or know that, a phase change actually uses a lot of energy. So you take advantage of that by inducing the phase change from the heat coming off of that. You can remove a lot of heat from a system. So this is for electronics, this is for engine systems, things like that. One of the problems with using two-phase flow like this is something called critical heat flux, where you've essentially pulled so much heat that you've trapped a wavy vapor layer in between the surface that you're trying to cool and the cooling fluid itself. And as that, the vapor doesn't actually transfer heat as well as the fluid. So you'll get the surface that you're trying to cool gets hotter and hotter, and then it creates more and more vapor, and then you have a runaway situation where your expensive equipment melts, and that's not good. So what we're actually, the flow boiling module is set up to simulate that, to actually let it happen and then cut it off before anything melts, theoretically. And then we image what it looks like at that point when it failed, when you had this thermal runaway. The graph that I have here, you can kind of see our imaging scheme, like how we are taking data. So we bring it up to different points, kind of hold it steady, image at that, and then there will be some point when we look at our temperature data where the temperature will just go crazy, it'll just spike off. And at about 125 C, we cut it off for safety. We have a whole bunch of safety circuits for that. That box actually up in the corner, or up in the top there with all those numbers on it, is our safety thermocouple cutoff box. It was done by grown-up engineers who like very, very controlled situation, because we're studying a failure situation that could get out of hand. But it's still very neat. So one of the biggest concerns in space is this kind of thermal runaway, is a situation where you lose, loss of coolant, things like that. That is very, very hard to deal with and control in space situations, because it's harder to contain fluids, you don't want things melting, you don't want vital systems failing. So this is actually extremely important research. And not a lot has been done researching this specific phenomenon. So this is a big contribution that Glenn is hoping to make to physical sciences community. Right, so these are some of the fluid loop support hardware. I assisted with this a little bit. Basically, that big bright blue module that you saw isn't the only part of the experiment. There's actually a whole set of systems that you have to heat the fluid up, you have to pump the fluid, filter the fluid, make sure everything going through there is a very, very controlled, very carefully monitored system. So that's the test module, as I had a couple of pictures of those before. But we also have a couple of things like the condenser array. Since we're doing both vapor, like steam and fluid, we want to be able to condense it back to just a fluid so that we can carefully control the amount of vapor that's in there. We also have an accumulator, which keeps the system at a constant pressure, theoretically, unless it's that accumulator, which you have to fight with sometimes, but that was an interesting experience with that. But also we have the FC72 pump and filtering system, which makes a horrifying sucking noise, and I helped set that up, and I thought it was broken a lot, but it actually functioned pretty well. And the filter is just there because you can't run, you have to make sure that any metal, from the pump that comes out, or any scraping, stuff like that, you don't want any of that in the system because that could just implode the whole thing. So I worked somewhat with the fluid loop, and I just wanted to include some of the pictures that I took when I was there. So what is FC72? I was actually quite interested in this chemical that we were using to do this fluid testing. It's actually an electronics coolant. It's dielectric, which means that it doesn't conduct. It has a very high breakdown, so it's very good for cooling electronics. It can go right on the electronic surface. It is extremely chemically stable, unless it's brought up above obscene temperatures and pressures, and then it can break down. But that's part of the control in our experiment, is making sure that things never get above certain temperatures and pressures. Another safety concern with us. But it has a very low boiling point, and that is important when you're trying to do boiling tests, because you don't necessarily want to sit there and wait to bring water, for instance, up to a boiling temperature or some kind of other fluid. This one, it actually boils at 56 degrees C, so that's just above room temperature, very easy to bring it there and control it, keep it within a nice temperature range. It's a fluorocarbon, and so that is another safety concern. We had to be very mindful of any spills and making sure that all of the FC72 is contained, because it is a potent greenhouse gas and evaporates quite quickly. So I learned a lot about chemical safety while I was there too. That was pretty interesting. One of the neat things about FC72, or Fluorinert, is that they've actually been using it in medical testing. I don't know if you saw a while back, they had mice or rats that they had submerged in a fluid that they were breathing. It was actually FC72. Oxygen is it dissolves very readily in this fluid, and they've been thinking about using it for burn victims who are having pulmonary edema, can't necessarily get oxygen into their lungs. In worst case scenario, they could fill them with fluid and be able to get oxygen to the patients, keep them alive. But I thought that was really neat. But because it has this property where it carries oxygen really well, we had to degas the system. Every time we ran it, we had to make sure that we pulled everything out, or we were going to get inconsistent test results, which you want to try to minimize. So one of the big roles that I played was setting up the data acquisition system for this fluid loop. I had never done wiring quite as you can see, it's a kind of intense amount of wiring, but it was actually really interesting because I got to learn about a lot of data acquisition in general, just that there's more to it than saying, okay, well, the temperature goes into the computer and we record it. You actually have to run it through something called a data acquisition system, which takes the signals, amplifies them, makes them into a viable signal for the computer to interpret. We were using National Instruments data acquisition. You may run into those in some of your physics classes, maybe if you take advanced physics, because there's a lot of past over here. But you create an interface yourself, basically, through a program called LabVIEW, which was another one of my responsibilities, where it's a lot of programming, a lot of hardware interface, which is something I'm very interested in. I'm very interested in low-level hardware, software interface, things like that. So this was a really good opportunity to learn how, what requirements these different sensors had, which ones needed voltage, which ones you shouldn't put voltage on, things like that, and actually developing the system and routing it through the computer. Did a lot of documentation too, which is extremely important. It sounds dull, but it's extremely important to learn proper documentation. And you'll start seeing this in your science classes, where they want you to write down, when you were doing setup, what did you do, what were your steps, how did you set things up. That'll be a very important skill if you want to go into the science fields, is documenting what you do and making sure that you have clear documentation. So I made these fun schematics that show you what each terminal was. And yeah, that was pretty much the data acquisition system. It took up a lot of my time when I was at Glenn. It took up probably 3 to 5 weeks just doing the wiring on this and learning about the systems and getting everything up and running. But it was very interesting. The system had a ton of sensors. I have some listed there. It had 15 piezoelectric pressure transducers, which are essentially just being able to monitor the pressure in the system. Those needed to be powered. The 23 type E thermocouples, those didn't need to be powered, but those needed to be amplified. There was all kinds of requirements that went into designing this system. It was really neat. So the second big system that I set up, that I was responsible for, was the camera system. When we were doing the flow boiling experiments, a big thing is correlating the data points that we're seeing with the heat transfer to the images that we take so that we can actually see, okay, well, we had critical heat flux here. What did that actually look like in the system? So what we use is actually a pretty small camera. We want to keep everything very small profile because it costs about $10,000 a kilogram to send things up to space. So they want everything as small profile, as compact as possible. And what my mentor had actually come upon and was that these small sort of CMOS cameras can actually be used as high frame rate cameras if you make the resolution low enough. So a lot of times, like your camera phone, it'll be 1080 or 4K. That's a lot of pixels, huge image data. But if you narrow that down significantly, I believe that we were using, it was 1080, but it was by 160 pixels, very small image resolution, and we were doing it in black and white. What you can do is you can image at an extremely high frame rate. Part of the big thing with the cameras was that when you're imaging at high frame rate, we were imaging at 2,000 frames per second, which isn't like insane. There's phantom cameras that do like 25,000, but we were still quite fast. One of the big concerns is that any kind of fluorescent light, any kind of incandescent light, you're going to see flicker. So this comes back to the strange blue glow that everything is that we had to actually use an LED that had very consistent, very monochromatic light, so that when you took the images, you didn't see any flicker and you got very crisp, right in the sensor's sensing range. It's very, it's very interesting. But yeah, so the camera, you can see that in this picture in the corner here, the camera is set up in a different location. This is actually me running a test on a fluorescent light to kind of show that there is that flicker. It was a demonstration to me to show what to avoid. But I thought it was kind of a nice picture. So to process this large amount of image data, we actually had a dedicated image acquisition system. In the actual flight model, there will be an imaging system that controls both data acquisition and image acquisition. They're still working out the details on how that's going to go. They're moving into engineering model now. But for ours, we had a dedicated imaging system. And one of the big reasons for that, and what actually got me really interested in radiation effects on computer hardware, was that this particular imaging system had been just absolutely totaled by radiation. They put it in, through radiation testing because they wanted to make sure that the hardware wouldn't fail after 10 years of space radiation. So this piece of equipment was mental because when you put computer hardware in radiation, it does very strange things. It's actually very difficult to predict what the behavior will be. So the system itself consists of a single board computer, which is a full i7, like it was 3.6 gigahertz i7 desktop, but it was this big. A frame grabber, which is how you interface the camera, especially when you're doing high-speed imaging, to the computer. It actually processes those images. And a very low power supply, because this imaging system is actually going to have to be hooked up to the power system on the International Space Station, so it has to be very low power ground. The software we were running it on Linux, because that is the most cooperative, but you can also run it on Windows 7, depending on your needs, depending on drivers, things like that. But we were using Linux, a very, very lean version of Linux called Lubuntu. And I was using it with this proprietary software for the frame grabber called XCAP. And you can kind of see in that picture what that sort of looks like. But yeah, it's a very, very tiny computer. It was very, very small. So now I'm going to talk a little bit about radiation effects on hardware, because that became like my favorite thing, especially after that summer. These images were taken before I was there. I didn't actually get to go and do this, which is sad, but this is the Radiation Effects Research Program proton gun. It is 200 mega electron volts, and basically they blast the hardware to simulate what would be like 10 years worth of radiation in space. Space is actually a very high radiation environment because you're not shielded by the magnetic field from the Earth, you're not shielded from anything, so you don't know what kind of particle strikes you're going to get on hardware. That's a huge problem for any kind of computer system or any kind of semiconductor-based thing that goes up into space. So one of the options that you can do to correct for this is you can just do tons of lead shielding. But as I mentioned before, if it's $10,000 a kilogram to send things up, how much heavy lead do you want to be sending up if something's very vital? Another thing you can do, they have developed some algorithms, some correction algorithms that will try to take that into account and make up for that, but at the same time, that's still not perfect. And I put an example up there. Solid-state hard drives are very important when you're doing large volumes of data, because a solid-state hard drive is much faster than a mechanical hard drive, and you want to get that data transferred as quickly as possible. But if you use a solid-state hard drive, you're actually risking losing the entirety of your data if one component on that drive gets hit by one radiation strike. So they're actually not using that. They really would like to use solid-state hard drives and faster equipment, but they're kind of limited to things that aren't as susceptible to radiation damage. I actually did a diagram of what happens to a MOSFET semiconductor when it's hit by a particle. It basically tears through the structure of the semiconductor, and it can deposit charge into the material. It can also short it to ground, which it could sometimes catch things on fire, which is not good. And that was really like, because this system, that is the exact same, that is the system that we use that is sitting there. But because the system had been irradiated, it was totally unpredictable. So sometimes you would look at it funny and it would blue screen. Sometimes you would touch it and it would blue screen. It did the strangest behavior. But that really got me interested, got me thinking about like what advances they could make, how they could make these systems more hard to radiation without increasing the weight, without increasing, the cost significantly. So this animation is actually images that I took this summer with the camera. This is the flow boiling module in critical heat flux. You can kind of see how that wavy vapor layer has developed. So there's this vapor that's stopping the fluid from actually cooling those two simulated heating plates on there. It was recorded at 2,000 frames per second. It actually whizzes by when you look at it, but it's playing back at 33 frames per second. So this one, I actually did not set up the camera system for this. This was the engineering model, but I did take these images. One of the responsibilities that I was given this summer was to run some tests actually on the engineering model, some calibration tests for the flow visualization module. This is actually a condensation experiment, and it's slightly related but unrelated to the flow boiling, and they're going to be joined together. Unfortunately, like I said, the visualization module was de-scoped, so it's not going to be going up. But these are some video, and PowerPoint doesn't like to play them, so there we go. These are quite big. So there's 3 cameras. And one of them is watching the inlet where the vapor is coming in. One of them is watching the middle where the vapor is starting to condense along the pipe. And then one of them is watching the outlet where everything has kind of started falling off and splashing. And this is just some nice, a lot clearer images because they were set up by an optics engineer. So, now that I've kind of talked about what I've done, I want to talk to you about how you can get involved at Glenn, because it was just an incredible experience, and I feel that if you can do it, you absolutely should do it. These are some of the links that take you. Intern.nasa.gov is where you want to go for your LRCIP internships, which is what I did. There's also Pathways, which is USA Jobs. That's a little bit different. That is, you work a specific job, and then it's kind of almost like a co-op, and then at the end of it they hire you. It's a very desirable position, so if you can go for that one too, that's one to go for as well. But if you'd like to have a summer experience, they also do fall internships and spring internships. It's intern.nasa.gov. And there's more information about it too. So this is how you apply. It's a little bit confusing, and when I was talking to some students about it, one thing I found was that they are having a hard time navigating through here and knowing what they should fill out and what they needed to do to get things moving on it. So if you go to the intern.nasa.gov website, you will see student opportunities. If you click on that, you'll see internships. You want to create an account with the OSSI, which is the One Stop Shopping Initiative. And then you can fill out, it'll take you to a screen where you can fill out your application. You want to be very careful when you're filling out everything. You want to make sure you fill everything out. They don't like it when you leave things blank. They also are kind of strange. You know, you're taught with your resumes that you kind of want to make sure that, you know, you're brief, you come across quickly. But with NASA, they want paragraphs. They want to know all about your life. So make sure you write them full sentences, paragraphs, really go into detail with like your past jobs, your past volunteer experience, like really tell them about it. And that's the most effective way, because you want to convey to them why they want, you know, you specifically out of, you know, hundreds of people that are applying for this position. Definitely have someone that you trust proofread your application. This is very important. Typos are just killer because it's so competitive. It seems kind of silly, but if you have a lot of typos in there, they might be like, well, this person, I don't know, they don't care enough to go over this. Make sure you proofread everything before you submit it. Absolutely. So they have kind of 6 major things that you need to fill out about yourself. They go into sub-menus. General information about yourself, your demographics, your position in school, your major, educational history, volunteer history, that kind of thing. And you kind of just go through and make sure you fill everything out real carefully and have someone proofread it for you. So the next step is to approach your professors and your professional contacts for recommendation letters. This is very important. You want to make sure that the person has something meaningful to say about you that isn't just like, oh, this person's great. You want these letters to be very good, and you want to approach people that you trust, people that you're confident that will give you a very good recommendation letter for this. They asked for 1. I would recommend more than 1. I did 3, but that really varies. I wouldn't just go with 1. More than 1's probably decent. And it's also a little bit strange because you don't send the letter to them. You'll actually have to go into the system once you've asked the person who you would like the letter from. You have to go into the system and send a request to them from the NASA website. So it's all electronic, and they want it through that system. The next step, after you've gotten your letters and you've filled out all your forms, is to search for opportunities. This is the most important one, that's easy to miss. So just because you've put your application in and submitted your application doesn't mean that they're just going to be like, oh, here, have a job. That you actually have to apply to specific opportunities. You start out by making your interest profile. One of the things that they ask for is what areas of study are you most interested in. You can pick up to 10. I would say go for all 10 because that'll give you the most. It'll show you the most opportunities possible with that. If you put those in, but broad range of interests. If you feel confident, like interested in something, I would actually put that in your interests because you may find an opportunity that you can work with that. The other thing is you have to apply to them each one individually, and how that process works is when you search for opportunities. You'll see them listed, you click on them, they'll give you a kind of a long description of what they expect from you, what the project is about, what they would like for you to have, and it's extremely important when you're responding to that you address specifically what they said in that job posting. Like specifically, like if they said, we want someone who knows Python, you say, I know Python. You want to specifically read through and address the points in that one. Don't just do a form letter where you say, I'm good at Excel. Like, no, don't do that. You want to make sure that you talk specifically to that particular opportunity. It's no more than 150 words, but that's how you apply to each one, is that you write a small paragraph kind of talking about your skills, speaking directly to the opportunity, and then you submit it, and then you can apply to up to 15 of them. So if you find multiple ones that are very interesting to you, it's usually helpful to not just have your heart set on one, but go for multiple ones. And finally, here are some interesting pictures that I took at Glenn. I just kind of wanted to share with you. Glenn is a very strange place because it's kind of like has everything is like the 80s, but what the 80s thought that the sci-fi future was going to be like. Because you have these kind of old buildings and then these crazy huge machines and like pipes everywhere. It was a very interesting experience. So some of the pictures that I took in the corner there, that is the supersonic wind tunnel. We were standing inside of it. It is massive. Then is the air in the middle. That is the airfoil for the supersonic wind tunnel. It is taller than a building, and we were also standing inside of there. Just the scale of everything at Glenn is kind of overwhelming. Over here on this side, these are the hot and cold engine test facility. They basically ice engines or broil engines, and over here are the control rooms for that. There's just so many buttons. It was really it was really cool to take these tours and to see all these facilities and to see what people were doing. One of the examples that I like to talk about how surreal it was being there was that in the morning I would go and get coffee in this little kitchen that was in this building that had a hole that was 500 feet deep, just like right over there. And it was as I was drinking my coffee, just like this 500-foot vacuum chamber. Like it was very weird. It was a very cool experience, and if you have the chance, I would 100% recommend that you apply, that you look into it, because it was fantastic.
Does everybody know where NASA Glen is? It's right by the airport. If you drive on 480 next to the airport, you can actually see the huge Quonset hut. What's in the Quonset hut?
It's a hangar. Actually, they have a couple of airplanes. They'll store engines, stuff like that in there. So, any questions?
Are you likely to go back?
I am likely to go back. This semester I'm not going to be working with the same group, but I might actually be working with a contractor that is working on the imaging system, so I'll be working with them still. So but I'm still kind of unsure about how that's going to go, but yeah, definitely.
Do you know, Aubrey, if NASA will take international students for internships?
I do not believe that they will. I feel like I've heard that was mentioned but they do actually have programs for international students. You'd have to look into it on the OSSI website.
Yeah, I've taken lots of groups on tours of NASA Glen, and sadly, in order to get security for the tour, if you're international, you cannot go in for a tour. So I was curious.
How much education do you need to start going for an NASA internship? Like what year, sophomore, junior?
I did it as a sophomore, so
Okay.
I would say it's a little harder for freshmen. There were some interns there that were freshmen that it was a little bit harder for them because they don't have some of the classes that would be more helpful. But I mean, if you want to go as a freshman and you feel confident, I mean, they will usually say what level of school they'd like you to have, but sophomore is usually sophomore, junior.
Okay.
Jake, did you have a question?
Oh, it was this question.
Any other questions for Aubrey?
Have you had any other internships, and how do they compare, if you have?
I actually have not. Well, other than with OpStem, and it's kind of a different type of internship. I feel like maybe this one has ruined me for other ones, but it was a very good experience.
Did they talk to you about if the liquid that you're using in there generalizes to other liquids going through something like this?
I believe that there are a couple of other coolants that they can use, but FC72 is preferred because of its
So they would be
dielectric
using
and its
that,
low boiling.
like in space.
In space, yeah. They would actually prefer to not use FC72 just because of some concerns with, they don't want it to get out into the, it has to be double contained and stuff like that. But this is really the best use for dielectric cooling like that right now.
Okay.
Are you surprised with the overall size of like the NASA Glen campus? Because I've been there multiple times and I didn't realize it went back that far.
It's insanely huge, yeah.
I was really surprised too.
Yeah, the first day I was there, I actually, I got there early and the guards didn't know what to do with me. So they were like, go find your building. And I was like, I don't know what, they're like, it's probably 3. I walk in 3, I'm like, it's not 3. And it's just walking around the campus trying to figure out where I'm going. It was, yeah.
What were you doing on NASA campus?
I've been there for a tour because I had to do it for something, via Eagle Scout, and then I went there when they had like their 15-year like open house or whatever. They only have it so periodically. I went to that too.
Anybody looking at doing an internship this summer?
No, this summer.
It's not anymore.
Next summer, maybe go to NASA?
Do it. This is awesome.
And I don't feel like I'm at Catholic school to
That's not necessarily the case though, because I have to say this one was the most intimidating one I applied to, and I was like, oh great, you know. But you can do it. You can do it.
You learn a lot of those things on the job.
Yeah.
Even when you started, like when I started my PhD work in physics, you go into the lab and you're like, you know, it's like you're looking at these things and you're like, how does somebody, and you catch the jargon and learn what's going on. Because you're working with this one thing 40 hours a week, this one thing. So you go in with a little bit of experience and they put you to work, and before long you feel you can talk very fluently about the project. So don't let Aubrey's fluency in this very cool thing make you feel like you can do it too.
Because I came in having no idea about anything with fluid physics. They were like,
Why-
how did you get the job? Yeah, you can.
Probably the electronics.
Yes.
Yeah.
What did you learn about programming when you were there?
So I learned a lot about LabVIEW programming, which is kind of it's a visual programming language where you kind of move blocks around. But I also learned a ton about Linux programming. Like I knew very little about Linux programming and at all before I came in, and I had to learn that. So.
When I used to work on a stripped down system.
Oh yeah, absolutely.
You'll find that when you work in a lab like this or in an experimental lab, that a lot of them are working with really stripped down basic systems because they have to really reconfigure everything to run their very proprietary stuff. So you get to learn a lot of really from some building blocks, which is really, really nice. They probably were much like the physics department at Ohio State, where the IT guys had to be able to run every computer system ever made. Yeah. Because there's so many different stripped down systems that are used to do this experimentation, but of course there's nothing off the shelf made for it.
Did you ever happen to do any work or see anything with I think it's the gear system that they have set up there, where it's to test the different atmospheres of different planets?
No, I didn't actually. No, I was kind of over with the like I was in the building where they have the vacuum chamber and stuff like that, but for the most part I was working over in microgravity. So.
How do they decelerate something in the big drop?
In the big drop, they actually have a huge cushion. Like it's not styrofoam pellets, but it's like a big bag that's filled with something, and they just catch it basically as it hits the bottom.
Oh.
It's kind of a big bean bag almost.
Oh.
Yeah.
Could it catch a person?
Probably. I don't know. I don't know if you probably still not have a good time. But they mostly want to make sure they decelerate the experiments enough so that things just don't smash when it hits the bottom. Yeah. I did some work with the 2.2 second drop tower, the one that's not in the vacuum as well. That one, it's up like a rickety flight of stairs and slightly terrifying because it sways in the wind. But like they also have that big bean bag at the bottom. It was cool.
That's where they send their interns up there.
Yeah, they did. There was the pod of interns up there. Oh, gotta wear the helmets. Yes.
How did the entire mentor thing work? Did they leave you on your alone for a while, or were they
So
always around
you worked pretty closely with your mentor. the way that ours worked is I had kind of an over mentor who would just collect interns. She had like 7 of us, and then she would distribute them to her engineers. So I worked with Jeffrey Mackey, who actually teaches physics 2 here. For most, so he was around a lot, but if he was busy, then I was passed off to the grad students who are national, NSTRF, what does that stand for? I don't know. They were grant students that were doing research there. So I was given to a student named Lucas O'Neill who's working on his PhD for transients in flow boiling, and so I helped him do a lot of work, and then if something broke or was on fire or crazy, I would call my mentor, and he would come fix it.
Is anything on fire?
No, but we did have some catastrophic pressure transducer failures where it would just be like fluid, and you're like, no, that's really expensive, not good to let out. So it's an interesting.
Well, there is one NSCRF, it's a National Study of Chemical Residues in Fish, but I don't think that's what it is.
NSTRF.
NSTRF.
NSTRF. I wish I don't know what that stands for, but there was 2 grad students that I worked with.
Oh, NASA Space Technology Research Fellows.
Yeah.
Questions? It's time to go. Be sure to thank Ollie. That will be available on YouTube, which you should attach.